today. My name is Pete Sylvester, and I come from the magical land of Canada, where we do silly things like hitting each other with sticks and running into one another, all on a gigantic sheet of ice. When I'm not doing that, I'm a database administrator. I work for a managed services organization called Pythian that unsurprisingly hires lots of other people. And together we collaborate and do technical things for companies who have logos. But I'm not here to talk with you about that today. Today I'm here to talk to you about MyRocks, which is the implementation of RocksDB as a storage engine for MySQL. You're going to notice here on the slide that Percona Server 5.7 is in bold, and I just wanted to note here that this talk is based on the Percona Server implementation. Your mileage may vary as you work with other folks at MySQL, be it the Facebook project specific for MySQL community or MariaDB 10.3. Now this is really interesting considering the fact that MyRocks brings us some new features, specifically the log structured merge index, which is giving us a higher degree of write optimization that we've seen previously with InnoDB. So a comparison of this is that when you're writing with InnoDB and you're going from memory space to disk, usually you're trying to achieve a way of ordering data and sorting it and optimizing it at the point that it goes from memory to disk. However, with RocksDB, things are working a little bit differently. You have log structured data. All of your changes are a single appended event into a log. And when the memory space fills to a certain capacity, it writes it directly to disk verbatim. And then other processes will come into play, and it's going to grab data, and it's going to move it down into a lower layer of the data, merging things in, sorting the data. It's going to do that over and over and over again into larger and larger portions of the data, which is going to help you achieve deferred write optimization. So again, big differences is instead of optimizing for reads directly when it goes to disk, you're deferring that into a later process, and this is what we call log structured merge. We're going to get into a lot more details about that as we go through the talk. That's just a high level approach. So I will be completely honest with you. My knowledge of log structured merge in RocksDB is actually very, very recent. I heard of the technology several times over various conferences that I had attended previously, but much like a lot of other technologies we hear about, generally don't dig in too deeply until something achieves a certain degree of relevancy. And for me, that happened in December of 2018 when Percona announced that they were deprecating TokuDB and was recommending that we should start exploring MyRocks. So that first grabbed my attention, and then I started looking at this and saying, okay, well, it's becoming part of core technologies such as CockroachDB, TiDB, and even other log structured merge technologies like Cassandra are starting to implement it as well. So when you look at this, it says, okay, well, maybe this is something we should dig into a little bit more. So one particular thing I found interesting when I started researching this is that usually when you start researching a new technology, you'll find that you usually have an overabundance of information that may be ambiguous or contradictory. But in this case, I actually found that there was a large absence of information that was available. It was highly fragmented, spread across multiple wikis, presentation slides, so on and so forth, a few blog posts. And that made it particularly difficult to put all the pieces together and figure out what RocksDB and MyRocks was all about. But once I had that, I figured it would be a good service to the community of sharing this knowledge, so I turned it into a 7-series blog post, and if you get a copy of the slides, you can get the links to it there. So that's where I first presented the information. It's also where I decided that I would actually turn this into an industry talk. Now, the blog post is approximately 27,000 words, so we're not going to be able to get into all of that today, but we're just going to do a small subset of that. We're going to be talking about how data moves into RocksDB, MyRocks specifically. We're going to be talking about how data moves out of it, and we're going to talk about specific configuration variables so you can optimize this process, and also certain metrics that you can use to help determine the impact of your configuration changes. So with that said, we can go ahead and get started with the first high-level concept, which is RocksDB, unlike InnoDB, is a key value store. Now this causes some people to take pause for a moment and kind of wonder whether or not this is a technology that's right for them, because usually we start thinking about key value stores, we start thinking of like distributed MapReduce functions in Erlang, and this is something that might scare a lot of people, but when you really think about it, it's not a strong departure from what we're working with today. Usually when you're working with InnoDB, you're making reference to a record and a table, and you're usually making reference to it via a primary key, and once you have access to the record, you're looking at the rest of the data. And in this case, it's really not all that different. You still have a key, you have a value, and then the only real addition here is that you have metadata, which has timestamp considering the fact that this is a log-oriented storage mechanism, right? So again, not a far departure from what we're already working with, and this is something that makes it easy to implement as a storage engine for MySQL. Now, where things start to change is when we talk about logical groupings of information. Now, when we're dealing with something like DB, we're dealing with schemas, tables, columns, rows, etc. There's an extra piece of the scope here when we start working with MyRocks, and this is where you have your column family. So you can actually assign indexes, multiple indexes, into a single column family. So when you create a table, usually you're going to make a reference to your primary key here, and you're going to have a comment specifying exactly which column family it's going to belong to. You also use similar comments when you're adding secondary keys. So you can take a whole table and all of its secondary keys and put them into the same column family, or distribute it into multiple column families, right? So what this gives you access to is a certain degree of configuration scope. So normally when we think of configuring MySQL, we're usually talking about global or session variables, but in this case, we've introduced the new scope of column family. So when you group all of this data together into its column families, each column family can have its own configuration, and we're talking about more than just compression or other types of metrics that you can apply. We're also talking about memory caches that are specific to that column family. Now, this is important because if you assign a certain cache to a column family, or say that a certain column family is supposed to have a certain amount of memory, and you're not paying attention and you start adding more and more and more column families, you're going to start using more and more memory, and you could potentially end up in an out-of-memory situation. So you have to pay attention to the fact that you now have a new configuration scope. So with that said, let's go ahead and take a look at data reads, or sorry, rather data writes. And the first thing that happens here is we have our data changes. And again, as I said earlier, we're dealing with log structured data changes. So you insert a record, and that becomes part of the log. You update the record, that becomes part of the log. You delete, that becomes part of the log. You're always dealing with an append. And these data changes are going into memory, and each change that occurs is also being written into a write-ahead log. Now, if you're familiar with Postgres, a write-ahead log is going to be something that you're already familiar with, but for those of us who are more familiar with MySQL and NoDB, this is going to be a lot like your NoDB redo log. So this is essentially what you're going to use to recover in the case of a crash. When it crashes, it just reads from the write-ahead log, and it knows what was written into memory at the time that your crash occurred. So it's going to keep writing data into memory to a certain point where it hits a threshold. By default, that threshold is 64 megs, and it's going to change your Mem table into what's called an immutable Mem table. And this basically says, okay, well, we have this segment of memory where data changes have occurred, and now this can no longer change. In order to deal with new data changes that are coming in, it actually establishes a new Mem table, rotates your write-ahead log, and it says, okay, well, now that this is no longer changing, we can actually start to push this down into the disk, into its own individual data file. Now, earlier, I mentioned that you have these changes and they get written to disk verbatim so that deferred write amplification can take it and resort it further on down the line. That's not necessarily true. There is at least one optimization that occurs at the initial flush, and that's deduplication. So as we talked about it earlier, all of these data changes that you have are appended records in the log, but you don't need to store all of this information. So in this diagram, I've noted that we have a single record. Its ID is 1. We've changed it a few times. We've deleted it. We've recreated it. But the only part of this is actually valid was the final result in the log. So it's going to take the whole log in memory. It's going to deduplicate it, and then it's going to push it down to disk. Any questions so far? Carlos?
Why is not done this step in memory? So if it's a value for the same ID, why is not just replaced in place?
I think it maybe helps to do that in MVCC, basically, so it can kind of keep track for what it may have been at a certain time, because it needs to keep track of if you started a transaction, it needs to know for repeatable read.
Okay, so
right. But by the time it gets to disk, it deduplicates, so you only have the latest value for the record. So there's a couple of variables that are very, very important for this initial flush and for the space that's being taken up in memory. So the first part of this is your write buffer size. Now this is a column family option, so this is something that gets assigned to every column family. So every column family is going to use write buffer size for its active mem table. This is where data is actually being written into memory first before it goes to disk. So this is saying that each mem table is going to be 64 megs. So if you don't change this value, you're going to assume that if you have one column family, you're going to be using 64 megs for active writing. The next one is your write buffers to merge. Now, as we said earlier, when you have an active mem table, when it's filled, it becomes immutable. Now, you don't have to have just one immutable mem table. You can actually have as many as you want. So the way the process would work, like for example, if you had 4 of these, it would start by writing your first 64 meg active mem table. Once it fills, it becomes immutable. It starts filling up the next. Then it becomes immutable. Repeat that process 4 times, and then you have 256 megs of space being consumed, and it says, okay, I have 4 immutable mem tables. We're now going to flush this down into disk. One thing you have to be aware of is that when that flush process starts, if it's unable to flush all of that information to disk by the time that your current active mem table fills up and tries to do its rotation, it will actually cause writes to delay, slow down, or even completely stop. So this is why I would recommend we may actually want to just keep this at first at the default value of 1, because you have 64 megs being flushed to disk in the same amount of time that you're trying to flush or try to push 64 megs of log data changes into memory. Okay? So the next one here is a database level configuration. This is called RocksDB write buffer size. And this is something that I think is incredibly important because personally, I don't like having unrestricted memory caches. So what this is saying is that if you have like 4 column families, all with 64 megs each, you could have a potential of using 256 megs of memory for your active write memory tables, right? But maybe perhaps that's too much. Maybe you don't want to dedicate that amount of space. Maybe you want to set a specific reservation in order to make sure you're not going over a specific memory threshold, and you can set that here. So basically, if you set this to 128 megs, it's going to keep an eye on all the mem tables in your system, make sure it doesn't exceed that threshold, and if it does, it's going to go ahead and initiate a flush in order to make sure that you're not taking up too much memory. Similarly, we also have a max wall size. So this is going to keep track of all the write-ahead logs in your system. It's going to make sure that if you get beyond a certain level of write-ahead logs on disk, it's going to cause a flush of all your mem tables and push it all down to disk. Now, I'd recommend not changing this default value, largely because if it does hit a cap, it's going to cause all of your memory tables to flush at that one point, which, depending on the sizes, that could be not exactly the best situation that you're looking for. So as you're making your changes for data that are going into memory and then eventually being flushed into disk, the metrics that you're really going to want to pay attention to are the 2 that are up at the top, which is your RocksDB mem table total, which is how much memory all of your mem tables are taking up, and most importantly, your RocksDB stall mem table limit slowdowns and stops. If you see this going up, it's possible that you may have to reconfigure memory tables in order to ensure that your flushes are occurring in the amount of time it takes to fill up 64 megs of logs on disk. Or I'm sorry, 64 megs of data changes in memory. Does anybody have any questions in regard to data going into memory and then being flushed to disk initially? Okay. So now we start to get into the magic of RocksDB, and that is compaction. And this is where all of your deferred write amplification occurs. Starting off at that L0 portion, which is where all of your data changes initially get flushed to disk, and then get restructured as they go down from L1, L2, and then finally down to the default maximum compaction layer of L6. So let's zoom in a little bit on the last process we were talking about, how your immutable mem tables get flushed to disk initially. So here we have 2 immutable mem tables. right, ranging of 100 to 250 and 0 to 150. And they are just going to be pushed to disk, just exactly as they are post-deduplication. And then you're going to see in your SSTs that you're going to have a range similar to what you have in your immutable mem tables. No big surprises here. But we really don't want to have overlap in our key range between files, because that means we may have to check more than one file in a compaction layer in order to successfully do a data read. So once level 0 hits a specific threshold, it's going to initialize a compaction thread, and it's going to select one of the files and say, okay, well, we're going to go ahead and start compacting this SST file. It's then going to go down to the next layer. It's going to say, okay, I need to find all of the files that potentially overlap with the file that I'm trying to compact at n+1 compaction layer. So in this case, we're going from 0 to 150, and it's selecting these two files here and here because they both overlap with the key range that's in the SST file that's going to be compacted. The next thing it's going to do is it's going to feed these into the compaction thread. It's going to sort the data, it's going to merge the data, it's going to deduplicate the data, and it's going to write a new file here, which will encapsulate the full range of the file that we're compacting and the overlapping files below. And that's why we see 0 to 200 here instead of the 0 to 150 that we're seeing here, because we have to, incorporate all the data that's in all the files that fall into the compaction scope. Once it's done, it has its new file, doesn't need the old ones anymore. It deletes them, and the compaction process has completed. Now this repeats over and over and over again as we work down our LSM tree, starting with a small piece of data at the top where our data is small, it's manageable, and then slowly moves it into larger and larger segments of data as it just goes down the tree through all your compaction levels. Any questions on this, sir?
You have records up to 300 in the level 1?
Sure.
Where do you get them from?
This was just an example. This is data that already existed on disk at the time the compaction occurred. Right. Any other questions about compaction? Igor?
How many levels can you get from level 1 up to?
Good thing you asked. We're actually going to cover that here in just a couple slides. Okay. So there are a couple of key metrics and variables that are associated with compaction. The first here is our compaction trigger, and it's really important to know how many levels you have, how big they can get, when they get compacted, and this is where all this gets configured. Now these are all column family options. I mean, you can configure this for logical groupings of data that you put into different column families. So the first one here is the level 0 file num compaction trigger. So once data gets flushed into its initial L0 compaction level, by default you can have 4 files there. Once you have 4, it's going to say, hey, okay, we need to start a compaction, and it's going to start compacting from L0 to L1. Then when you get to L1, this is where you actually get to specify how many bytes are in your level. And this is where the default value is 256. And then you have max bytes for level multiplier, where it says, okay, for each compaction level going down, this is how many times larger the next compaction layer is going to be. So the default is 10. So you start with 256 megs, then you move down to 2.5 gigs, so on and so forth, until you get down to your 7th compaction layer, L6, which could potentially be 24.5 terabytes. And then you can specify how many levels of compaction you want using the column family option num levels. It starts off with 7. Honestly, I don't think you're going to need to add any more than that. I think 25 terabytes is usually going to be large enough for a single instance. Your experiences may vary. But this is the default value that you get when you first install Percona with MyRocks. So once you know how big your compaction levels are, you can also specify how big you want your SST files to be. So level 0, it doesn't really follow a designated file size, because when you're dealing with information that's in your immutable mem table, it's 64 megs, but after deduplication, if you're dealing with a lot of updates and deletes and so on, it can be very small, down to like a single meg or even 2 megs in some sysbench tests that I ran. So it's just going to be the size of your deduplicated mem tables. Once you get down to level 1, it's going to start with a default value of 64 megs. And then it's going to say, for target size multiplier, this is how much bigger each file will be as we move down from compaction layer to compaction layer. Now, my thought on this is with my testing, I was hesitant to increase the multiplier for each compaction level. The reason being is that there are a certain number of threads that you can apply to compaction. So the larger the file, the larger it's going to take, or the longer it's going to take to compact. So you want to make sure you can get through your compaction processes fairly quickly so that those threads can be made available to start compacting different layers as needed. Now, the trade-off here is that the smaller your files, the more you're going to have to go through compaction because you're dealing with smaller segments of data for each compaction process. You're going to have to do more of them, but they are going to be faster.
So the multiplier is 1?
The multiplier is 1 by default.
Okay.
Now I know with Cassandra it's different.
It's 10.
Yes, I know. So this variable, a RocksDB max background jobs, actually impacts both the initial flush and compaction. This actually used to be 2 variables, one for initial flushes and one for compaction. It was 1 each. Now they combined it into 1 variable where the value is 2. So you would hope that one thread would always be available for your initial data flush and that a second one would be available for compaction processes. Now I would highly recommend increasing this because one of the big advantages that you get over RocksDB over other LSM engines is that you can have multi-threaded compaction, with the only exception being L0 to L1. After that, it can be fully multi-threaded. So I would take some time to increase that variable. Now, this is another important one being RocksDB max SubCompactions. As I just noted, the compaction from L0 to L1 is single-threaded. However, you can parallelize that process with SubCompactions. So I would also recommend increasing this variable because you want to make sure that you're moving data out of L0 into L1 as quickly as possible, because obviously if things hit thresholds, it can cause slowdowns, it can cause stops. So again, just another variable you may want to consider increasing. As it goes for metrics for compaction, there's a few things you're going to want to take a look at. You have metrics that show you when your compactions are not operating fast enough, when you're getting slowdowns, when you're getting stops. You can also check your compaction stats, your column family stats table to let you know how many compactions are currently pending. So if the queue is building up and your threads aren't addressing it quickly enough, you can at least identify where exactly that's occurring. And there's also 3 whole information schema tables that are fully dedicated to compaction, being your compaction stats, DDL, and index file map, which allows you to determine what files are associated with what column family. So, any other questions on compaction before we move on? Okay. So, the only downside to compaction as we move through here, you'll notice that you are going to have multiple copies of your data. You'll have it initially in L0, then move down to L1, then move down to L2. And if there's a change that occurs after the fact, your old data might be in L4, but your new data is in L0. So you have multiple copies of your data, and there needs to be a way to make this a little bit more manageable. And there's 2 key ways that MyRocks/RocksDB deals with that, and that's compression and bloom filters. So just a quick show of hands, is there anybody here who's not familiar with bloom filtering? Okay. So this is a really, really basic example of what a bloom filter is. It's basically just a quick way of determining set membership. So the first thing you do is you start off with an array or multiple arrays of zeros, and as you insert new records, it basically puts it through a multi-hash. So for example, if we were to insert X and have it go through our hash, it might say, okay, well, we need to change addresses 2, 5, and this one here to 1. And so on and so forth for the different values. So when you come back and you want to check if something is part of set membership, you're going to run it through the same hashes. So in this example, we're going to W and say, hey, run it through the same hashes. It says, okay, well, if W is here, it's going to be addressed here, here, and here in the array. And at this point, we know that this is 0. It's never been toggled. So now we know that it's not a member of the set. Now, bloom filtering is also really, really important with MyRocks because if you remove members from the set, you never want to actually change the toggles of the bloom filter array because hash collisions can occur. Just because this is being removed doesn't mean that something else wouldn't toggle the same portions of the array. So the good news here is that when you're dealing with MyRocks and you're dealing with compaction, files are being created or deleted. They're never being updated. And that's what makes Bloom filters incredibly handy when you're dealing with MyRocks specifically. There's only really one variable that you deal with when it comes to Bloom filtering, and that's simply turning it on or off. You're going to notice here that the configuration of this is a little bit strange. You have to start with your default column family options, with your block-based table factory, and then you have to specify the filter policy all within a single call, which makes the syntax a little strange. There's actually some really good blogs by Mark Callahan that address this, so you can get some good examples out there. So if you want to enable it, this is effectively how you do that. Your only real metric is to say how many times was my Bloom filter useful. So you can compare this against your various MySQL handlers or com-select, compare the two and say, okay, well, how many times did I actually get a point where a Bloom filter successfully negated a file check as part of a data read?
False positives and false negatives.
Yeah, it can tell you if something is definitely not in a set, but it can tell you if something is maybe in a set. Right. Sir?
The statistics you mentioned are global for MySQL. So how do you get only for this engine?
That's actually a very, very good point. I'm pretty sure that there are other metrics that you can use for reads against RocksDB. However, I don't know what they are off the top of my head. So another thing that we do to make this a little bit more manageable is to make sure that we're employing compression. This is another really big key feature that draws a lot of people to MyRocks and RocksDB. There are multiple forms of compression that are available, and you can very easily check what versions of compression are supported for your particular installation of Percona server. You just check the log and it's right there. So you can just go there and find out exactly which ones you can use. If there's one you'd like to add, you can install it and Percona will pick it up. So the reason why this is really popular with people who are trying to evaluate this for POC is because it does compress a lot better than InnoDB, 3 to 4 times better than uncompressed, twice as good as compressed InnoDB, and you don't really get a whole lot of the same performance penalties that you would typically see with InnoDB. When it comes to configuration, with your variables, you have several different variables you can use. You can say, hey, I want to compress my column family right across the board the same way. Maybe I want to do something different with the bottommost compaction layer. But the one I particularly like is the compression per level. So you can actually specify with a delimited, a colon delimited list here saying for each compaction layer, I want to use a specific form of compression. And the recommendation here is for your first 2 compaction layers to make sure you're not using any compression at all. Again, single threaded from L0 to L1. It's a place where you can get a bit of a bottleneck and prevent writes from occurring. So don't have compression as part of that. Make sure it doesn't have any kind of overhead. Let it do what it needs to do as quickly as it possibly can. When you get down into L1 and greater, you can start implementing compression and then use your highest form of compression when you get down into your bottommost compaction layer. So, a quick word. When it comes to data capacity planning, we know it's something that's difficult, especially if it's something that's got out of control. We have a growing data set, we have a specific amount of disk space, and people have a tendency to panic when this happens. I've actually seen production cases where people have implemented non-standard storage engines without taking the limitations into consideration, moving away from InnoDB, and then it doesn't really work all that well for them. In fact, I've actually had another client of mine recently reach out and say, hey, we want to try MyRocks simply because we just want to compress our data set. And I had to have a long conversation with them about taking the limitations into consideration. So anytime we implement a storage engine based off of a single feature without taking the limitations into consideration, God kills a kitty. So we don't want to have that happen. So any questions on compressions or Bloom filtering before we go on to reads?
So one thing, don't you need extra space available for the compaction stage?
Are you talking about decompressing the data and then moving it through? It does a lot of that in memory, actually.
Okay.
So it reads the compressed data.
So So my saying is like, my background is like what Cassandra does, it reallocates the space for the new level preemptively. So that space is taken immediately, and then so during a period of time while compaction is happening, you are using the space twice for that given compaction.
Yeah. While it's merging, it's reading data from two files,
Right.
and then it's writing to another file. So at that point, before it deletes the old files, it's using more space.
Right.
So yeah, so that might offset the, but I don't know how the other engines work.
Right. So unfortunately, I don't have a good answer for you on that, but we can always talk about that a little bit later on and see if we can't dig in and find out. Any other questions about compression or Bloom filters? Okay. So the next part of this is what we've basically covered, getting data into MyRocks. Now we need to talk about getting data out. And this is where we actually introduce our block cache, which is very similar to your NODB buffer pool in the sense that it's a large global buffer. All of the column families use the same one, and it is specifically used for reads. So you have your read process comes in, and much like NODB, the first thing it's going to do is going to go to memory and say, is this available in my memory cache? And if it does, it's just going to load it and send it to the higher architectures of MySQL in order to create your result set. If not, it's going to go to your Mem Tables, and then if it's not found there, it's actually going to go to disk space, which we'll zoom in on that. And let's say, hypothetically speaking, we have a read process that wants to read from ID 200. The first thing it's going to do is going to go to the highest level of compaction, which is L0, and it's going to say, okay, well, are there any files here that have a range where this ID would fall into place? Now in this case, yes, we're looking for 200. We have one file where you have 100 to 250, and then the other one is invalid because obviously the range falls outside of the value that we're looking at. So it's going to read that, and let's just assume that this has a Bloom filter associated with it. The next step is it's going to take your Bloom filter, and it's going to move all of the entire array for your Bloom filter. It's going to move it into the block cache, and then it's going to use that to help determine set membership. It's going to say, okay, well, is it in the SST file? And it's going to say, okay, well, maybe, and then if so, we can read from it, and maybe we'll find it, and maybe we won't. But if not, it will say, okay, it's not here, move on to your next compaction layer. And then it's going to go through, and repeat that process until it finds something, and once it's found it, it's going to put it in the block cache, and then once again, it's going to go up to a higher architectural layer within MySQL in order to provide you your result set. So when it comes to configuring this, you have a global variable for RocksDB block cache. Now again, this is something that applies to all column families. This is not column family specific. You're going to see that my recommendation here is for 60 to 75, and this is something that is not as large as what you might configure an NODB buffer pool for, because you have to remember, your memory caches for reads and writes are isolated, and your write buffers can change depending on the number of column families that you use. So you're going to want to be a little bit more conservative with this and then reconfigure based off of the metrics that you have visibility for. Now, this is one feature that I really like, and this is called the simulation cache. And this is something that can be really beneficial for you, especially when dealing with memory configuration. So what the simulation cache is let's say your block cache is approximately 100 gigs, something like that, on a 128 gig server, and you find that you're not getting the hit ratio that you want. Maybe you want it to be somewhat larger. You can actually use your simulation cache to say, okay, well, if this is 110 gigs, what would my hit ratio be? All it does is store the keys, doesn't store any values, and that's why it only takes roughly about 2% of the designated value. So conversely, let's say you're getting 100% hit ratio, and you want to say, okay, well, my read cache is doing really great, but maybe I want to have more memory allocated for my writes. Okay, so these are isolated, so I can set my simulation cache and say, okay, well, we're at 100 gigs. If I took this down to 80, would I still have a same high hit ratio? If so, I can reconfigure, make more memory space available for active and immutable Mem Tables, and now I'm saving read caching in order to make more space for write caching. The metrics that are associated with this, first are your block cache data hit versus miss. Very simple, Matthias?
I have a question on the previous slide.
Sure.
It says it's non-dynamic, so you have to restart.
You do have to restart, yes.
But wouldn't that reset your cache ratios?
Yeah, I mean, you'd have to record that prior to.
Okay.
Yeah. So obviously your metrics here allow you to see how visible your hits and misses are in your block cache. It also allows you to see where your hits are getting, because you can see here you can get from L0, L1. Obviously, it's more optimal if you want to get reads from higher compaction layers, because obviously the higher up it is, the less it has to check, because it starts at the highest one, moves down from one to the other, to the other, to the other, until it hits the bottom. So you can use this to get visibility into where the hits are occurring, assuming it has to go to disk. If this isn't occurring very often, maybe perhaps you can consider resizing L0 or L1 so you have a larger active data set on disk. Another important thing to note is that when it comes to your simulation cache, this is the first and only metric that I've found where you absolutely positively need to pull this from show engine RocksDB status. Everything else can be found either in a global variable or a global status or something like that, but this one you actually have to go to RocksDB status for. I'm not exactly sure why that is, but you will see two entries there for RocksDB sim block cache hit and miss, and that's the only place you can find it. That took me a little while to figure out. So any questions on the mechanics before we start talking about use cases?
If during the read you find several versions of the data, what does it handle?
It will stop at the highest compaction layer where it finds the data.
Even if on the lower version is a more recent?
The more recent version would be at the top. Because remember, data is going in, starting off at memory, then it starts at L0, then it gets compacted down to L1.
Okay, so I was thinking the levels, yeah. So
Right.
Yeah, okay.
That's right.
So it's deduplicated, so it cannot have multiple versions at the same level.
Correct. So you can have multiple versions at L0 because it's just being dumped directly to disk at that point. So you might have to check multiple files at L0, but beyond that, when you get to L1, L2, there's no key overlap between your files.
How does then on deletion there?
So once the compaction process is completed, it knows what files it's compacted, and at that point it's going to delete them. And however, if you have a transaction that's open, that's leveraging data that's in those files, it will have a blocker on it saying, hey, don't delete this right now, wait for a transaction. Transaction ends, the lock gets removed, and there's a cleanup process that comes around periodically and checks to say, okay, well, are there any files I can get rid of now?
Okay.
Okay. Okay, so we know how it works. I know I've thrown a ton of data at you. I would say that if there's anything you want to recap on, check the blog post, make comments. I'd be happy to continue the conversation. But right now we can cover when should we use this, when should we not, what are the advantages, what are the disadvantages. So first off, the obvious one is that we're write optimized. We write in memory, we get the memory to disk as quickly as possible. We clean it up once it's on disk. We don't really worry about organizing the data as part of that initial flush from memory to disk. Obviously we have compression. It compresses better than InnoDB, but obviously we have to take the limitations into consideration. Don't let God kill the kitty. It does have certain tests where it will work better when you have an active data set larger than the amount of physical memory that you have in your system. Now this is something from the Percona performance blog by Vadim, and he did some testing, and this is his jitter plot where they were using a throughput of transactions per second versus the amount of memory that was on disk. And you can see that as the active data set fit more and more on memory, InnoDB did act a little bit more performant, but when you're further on the left side of the graph, MyRocks performance was fairly consistent across the board. So backups, this is something that actually up until very recently was on the disadvantages slide, and only just a couple weeks ago got moved to advantages. There was a huge problem with TokuDB where it would try to, basically extra backup was unable to back up a system with both InnoDB and TokuDB. You would effectively have to stop MySQL and take a snapshot of your disk in order to get a consistent backup. However, up until recently you had the same problem with MyRocks, but now they've actually created a new version, 8.06, where when you run a backup, it will create a consistent backup of both MyRocks and InnoDB. So if you're using both, you're going to be just fine. When it comes to your disadvantages, I think the pretty obvious one here is range lookups. You are dealing with a key value store. So if you're selecting star from table where key between values x and y, you really can't use a Bloom filter for that. I mean, because if you're working with a decimal, I mean, you could have to check thousands of values in a Bloom filter to determine what is and what is not in there. So if you are doing a range lookup, you won't be able to use your Bloom filters. You will have to pull a lot more data into memory for evaluation and so on and so forth. It should be said that if you are using range values, this is not something that would completely disqualify MyRocks because it does have some optimizations in there to deal with range scans over key value. There is a really great blog post that was written by the folks over at CockroachDB explaining that in a bit more detail. There is some reduced MySQL functionality. For me, not having online DDL isn't really a deal breaker because we do have tools like PT Online Schema Change and Ghost. Foreign keys, that's going to depend on your perspective. If you're a schema architect or a developer, perhaps you want to have foreign keys in order to preserve your relationships. Personally, as an admin, I see them as a lot of overhead, so for me, not necessarily a deal breaker. With transportable table spaces, it's one of those things where you're not really going to miss it until you need it. So make sure that you're kind of taking that into consideration, make sure you're keeping an eye on your data set size. And then obviously you have no select for update when using repeatable read as your isolation level, but there is a lot of talk about this within the MyRocks blog, so on and so forth. It's something that they're actively working on, so I'm hoping it's something we'll see resolved in the near future. So the bottom line here is that if you're using a large OLTP data set that does not necessarily fit into memory, this may be a good situation for you, so long as you also have a write-intensive workload and a high concurrency read. That doesn't necessarily filter specifically on range, so you can take advantage of the Bloom filters that are there in RocksDB. So if you have all three of these, you should definitely consider it. But you know, if you're missing one or two of these, obviously it's something you should take into consideration. Check the mechanics, read the blog posts, so on and so forth, and find out whether or not this may be something for you. I know we've gone through a lot of information. Does anybody have any questions?
Can you give a concrete example for the usage?
So like a concrete use case?
Yeah.
What I can do is I can actually try to find some of the white papers and I can try to send them to you if you like. I mean, because right now we're a little short on time.
A concrete example, Facebook.
Yeah, I mean, Instagram.
Yeah, but Facebook what? I mean, do they keep the posts in there or
Yes.
likes?
Their entire user DB draft is in RocksDB.
Aha.
So they moved everything over in 2018. They moved everything over. They have blog posts and conference presentations about that, and they saved about 50% of this space.
I believe Facebook Messenger also.
Yes.
They migrated recently.
Yeah.
Okay,
It's
thanks.
write once, read many kind of use cases.
Yeah, that's a good way of looking at it, yeah.
Would it be an idea to have like your master in your topology run RocksDB and then replicate it over to InnoDB?
No, I would actually recommend replicating from MyRocks to MyRocks because one of the features that we didn't have time to discuss here is that you do have a read-free replication option with MyRocks.
Okay.
Any other question? Pat?
MySQL But is consistent
Yes.
between both engines.
I believe it is. I'd have to double check though.
Okay.
Thank you very much.